Consider a piece of material with the original length L being bent in a shape of circular arc. The circular arc has a radius of curvature ρ. For this piece of material, some portion of this material is compressed, while some portion of the material is being elongated. As you can see, the length of this arc must be smaller than the length of this arc. That means at some position of the material is compressed, while at another position of the material, say here, the material could be elongated. Actually, for a piece of material under the pure bending, there must be a neutral plane, which means no matter how you bend this material, on this neutral plane, the length is still the original length L. And this is the boundary of the compressed region and the elongated region. On this neutral plane, there is no axial strain, while above the neutral plane, if the material is bent like this, then this part will be compressed, while the lower part will be in tension because it is elongated. It is longer than the arc length of the neutral plane. Actually, if we observe the cross-section of the material, we can see that the neutral plane is like this. At this moment, we have no idea about where is the neutral plane, what is the properties of the neutral plane. So let's derive the formula one by one. Set y equals to 0 at the neutral plane. That is, we put the origin on the neutral plane, then at this neutral plane, y equals to 0. If we set the radius of curvature as the distance from center of the curvature to the neutral plane. The original length of the material, which is the length of the neutral plane, is given by L equals to rho theta, where theta is the angle subtended by the center as well as the end of the material. Then the length at different position of the material, say y. If y is positive, that means we are talking about the material which is in the compressive region. If we say it is y, okay. The length at y is given by L prime equals to rho minus y times theta. That is, the distance from center of the curvature to any position y is given by rho minus y. So this is rho minus y. So the length at any position y is given by L prime equals to rho minus y times theta. Still remember our axial strain definition, which is epsilon x equals to the change of length divided by the original length. The change of length is given by L prime minus L divided by L, which equals to rho minus y theta minus rho theta divided by rho theta. The answer is minus y divided by rho. Consequently, we can say the axial strain epsilon x at any position y inside the piece of material is given by negative y divided by rho.